ir lá? Estamos no ar? Beleza. Dia 3.
Isso, último dia.
Chegamos ao dia 3, último dia. Bom, gente, a gente tá aqui, né? Último dia de Good Morning Simulation.
Isso.
Primeira edição que a gente faz na América Latina. Garbim, conta um pouquinho do que foi falado, o que o Hassan contou nesse dia 2, né? Faz um resumo pra gente do que foi falado no dia 2. Primeiro, antes de você falar, quem não conseguiu acompanhar ao vivo, obviamente está disponível, vai estar disponível para vocês assistirem no dia 1, dia 2, dia 3, depois vai estar pronto sob demanda, tá? Então, mas, obviamente, a gente quer que hoje você assista o dia 3 e depois você pode voltar e assistir as outras edições. Mas fala um pouquinho o que foi falado no dia 2.
Vamos lá. O Hassan, ele tem um grande conhecimento nessa parte de cálculo de eletromagnetismo, ou seja, ele abordou aplicações tanto do eletromagnetismo de baixa quanto de alta frequência, né? Aplicação de simulação em motores, rotores, compressores, por exemplo, como também em alta frequência, que é principalmente antenas. O Hassan já trabalha conosco já há um bom tempo, tem um grande conhecimento, tem doutorado no assunto, ou seja, ele deu um overview, né, uma visão geral de como é esse tipo de aplicação, que é o CST para a indústria.
Legal. Bom, e hoje no dia 3, queria que você fizesse um resumo, um spoiler, do que o Ramesh vai falar. Né?
Joia.
É o outro especialista que nós temos aqui.
Ah,
a gente está
Ramesh...
aproveitando que esses gringos vieram para cá e a gente está sugando tudo que eles têm de conhecimento.
Ele já trabalha conosco já há mais de 25 anos, né? Ele tem um grande conhecimento nessa parte de cálculo, tanto cálculo estrutural quanto cálculo de escoamento de fluido. Ou seja, hoje o Ramesh ele vai abordar os mais diferentes métodos matemáticos, como elementos finitos, volumes finitos, diferenças finitas, elementos de contorno, que são métodos matemáticos para simular fenômenos físicos, ruído, fluido, estrutural, né? Esse efeito de interação fluido-estrutura, que é o portfólio Simulha, que dentro do portfólio Simulha tem uma gama muito grande de softwares que nós chamamos de solvers. Tem diversos solvers para diversos tipos de aplicação, então ele vai dar exatamente uma visão daquilo que nós temos já como tecnologia, que já está totalmente consolidada, e mostrar como é possível reduzir custos desenvolvendo componentes cada vez mais leves, eficientes e inovadores.
Uma coisa que eu falei no primeiro dia, que eu acho que é importante reforçar, é que para a gente, não importa o tamanho da sua empresa, não importa se a sua empresa é super grande e ultra complexa ou se a sua empresa é menor, a gente entende que simulação, prototipagem virtual, mod sim, que a gente fala tanto, é muito importante para você conseguir aumentar a velocidade do time to market, reduzir custo e ter uma assertividade maior daquilo que você está imaginando entregar para o mercado. Então, de novo, não importa o tamanho da sua empresa, esse conteúdo é muito importante, é muito interessante para você. Então,
Joia.
Vamos deixar quem manja falar.
Vamos deixar o Ramesh aí.
Depois, daqui a pouco, a gente volta para fazer um resumo geral para vocês, tá bom? Valeu, pessoal.
Um abraço.
Welcome everyone, and thanks for joining us today on this presentation titled Simulation for SolidWorks Users. So today you're going to get a preview of both our desktop as well as our cloud solutions when it comes to simulation. So if you look at how Dassault Systèmes as a company has invested in acquisitions of simulation technology over the years, like it started all with SolidWorks simulation, CATIA analysis back in the year 2000, or even before that, right? And the whole idea was actually to offer designer level simulation to the CAD base. But over the years, you can see there have been several key acquisitions, such as Abacus, such as CST Studio, and the goal was to offer not just designer level simulation, but offer multi-physics, multi-scalable system level simulations for all user personas, and also designers, engineers, and analysts can actually do the different types of simulations to get the job done. Now, if you break down our simulation portfolio, it really falls into three simple buckets. The first one is the SolidWorks desktop simulation portfolio, which is really geared towards addressing the needs of designers and engineers. And with this portfolio, you can really look at solving physics such as motion, rigid body kinematics and dynamics, structural simulation, computational fluid dynamics, and plastics injection molding simulation softwares. Then we also have cloud-enabled simulation, which goes a little bit, deeper into addressing the needs of, anywhere from engineers to analysts. And with this portfolio, we can really look at doing structural simulation, fluid simulation, and even electromagnetic simulation. So again, this is based on the Abacus technology, as you may be aware of. And again, electromagnetic simulation is a new physics, a new type of simulation that we are now offering for SolidWorks users. We also have the desktop, Simulate Desktop, which is Abacus CAE and CST Studio Suite. So again, if cloud, we offer the technology on cloud, and if cloud is not an option, you can always, the same technology is available on the Simulate desktop portfolio. Let's take a look at SolidWorks Desktop, what it can do real quickly, what it means for designers and engineers to be using SolidWorks simulation. Now, the first thing is to understand that there are two pillars of SolidWorks Desktop simulation. One is the integration with CAD, which allows you to design and simulate side by side. The other one is to actually do design space exploration, right? As a designer, as an engineer, you're using SolidWorks to create your designs, but at the same time, let's say you're tasked with it actually getting to the optimal design as quickly as possible. So design space exploration is in terms of using optimization tools, can really automate your design iteration process and help you get from a baseline to an optimal design as quickly as possible. Now, these two pillars together help to answer that fundamental question: how do we know that we have the best design? So let's take a look at a few examples. So this is SolidWorks simulation, an example for beam splice, right? I mean, how do you know, for example, 32 bolts or 18 bolts or 44 bolts can get the job done? But everything's based on a certain criteria we are after. So basically, in this case, we're looking at a factor of safety of greater than 2.0 in each of the bolt. Okay, so how do we go about doing this in a traditional way? We would actually make a prototype and test if 32 or 18 or 44 bolts will work as expected. But with simulation, we can get the same answers virtually, right, without making even a single prototype. That's where the beauty of simulation is. In this case, it's just illustrating the image on the right side. It's showing you that the 44 bolt configuration is the one that actually gets the job done, where the factor of safety in each bolt is at least a 2.1. Okay, so again, the whole idea of using SolidWorks Desktop, which is CAD integrated, and which is a great tool for design space exploration as well, is to hone in on the best design, test multiple designs, because the more designs you can actually test, simulate, the more data you're getting on your design's performance, and the more data you get, the better design decisions you can make end of the day. If you take a look at different types of physics, like in this piping example, we are looking at a long pipe, a short pipe, or a short pipe with vortex. How do we know which is the best design, right? Well, but what we know is from a system requirement, we want to get equal flow rates on either side of the outlet. Okay, so you can have the fluid is coming from the left side, let's say it's entering the pipe, and then it gets it's splitting up on the right hand into two different outlets. So we want to accomplish equal flow rates on both ends. How do we go about doing that? Well, simulation is the key, right? What's the other option? We can always make a prototype, and then we can actually go ahead and test the prototype and see if we're getting those equal flow rates, but it's going to cost you a lot of time and money. So the beauty of simulation is to see, to basically analyze these three different designs and see which design is the best. Obviously, the short pipe or the vortex seems to be the best design here, because we are really looking at getting that equal flow rates on either end of the outlets. Okay. Another type of physics, which is motion simulation. So this is an actuator rack. So you can see this video. The vertical rack system is being lifted up through an actuator device, and so the question could be, what size actuator do I need to get the job done? And so simulation can come in and say, okay, you want to lift it by, you have a certain stroke length, here is the maximum force requirement for the system, And then you can come in and look up this actuator chart to determine what size actuator you need for this particular design of the lifting rack system. And lastly, again, different types of physics. When you're doing injection molding simulation, the key question is your plastics part manufacturable, right? A lot of times you can use the tool to identify key manufacturability issues, such as, is it going to fill in the first place? Is the mold going to fill in the first place? Is it going to warp? The final manufactured part, is it going to warp? So, or is it going to be a lot of volumetric shrinkage that could be more of an aesthetic thing? Whatever the case might be, right? Simulation can actually come in and help you simulate those scenarios without you having to cut metal or make a mold and then test it out in the real life. So again, we are talking about, let's say, getting a window inside a mold without even building your injection molding mold. So it's a great way to understand, what is the best design. If the design that the first design doesn't work, then obviously you can make changes and move to design B, which can, and then do the simulation again to see if that design B works as expected. All right, so that is kind of a quick introduction to SolidWorks simulation desktop solutions. Again, very simple to use, different types of physics. The whole idea is to explore multiple designs, analyze the physics, and see what the best design is you want to go with end of the day. Let's talk a little bit, about Abacus, or cloud-enabled simulation. Right, so again, Abacus, as you all know, is the renowned, it's the world leader when it comes to structural simulation. So let's take a look at what it can do with structures and durability simulations. So the first thing to note is it's an industry leading solver. Okay, so this video illustrates or talks for itself. You can see all the high-end application simulations that we can do with Abacus Solver, and even manufacturability simulations such as blow molding simulation, thermoforming simulations, and a lot more. So again, Abacus is an FEA and a multi-physics solver, which actually is used across a wide variety of industries to solve from simple to very complex type of applications. And you can see that these set of videos clearly illustrate some very complex multi-physics applications. Okay, what else can we do with Abacus? Well, it's a powerful nonlinear analysis tool. It's a powerful nonlinear analysis tool. Some of the applications that are illustrated here clearly show the power of a column actually buckling and folding up on itself. That's a very complex physics, even though it looks pretty straightforward. There's so much physics going on, and you can see some of the other applications which I really like. The one on the lower right side, you can see it's an umbilical type of scenario where there's a lot of contacts going on, and that's what Abacus is really powerful about. Is to simulate these type of contacts, we don't have to, as a user, define those contacts up front or do a guesswork. Abacus has generalized contact, where we just turn on the general contact, and all these complex interactions, physical interactions that could take place between multiple parts of the assembly is all taken care of. So it's a super easy and intuitive way to simulate something complex when it comes to contacts. All right, how about explicit analysis, right? I mean, a lot of times, you have very fast dynamic events that you need to capture with simulation. So you can see examples, some very high energy collisions, impact, drop tests. This requires the use of what we call as an explicit solver. You can even take an entire assembly and put it through an explicit solver. You can do a crank crush, which is a very highly dynamic event. So these examples just illustrating how you can actually use Abacus to solve various kinds of nonlinear and also explicit simulations, as illustrated here. All right, so this example I like really, because of the fact that now we are talking about using a combination of fluids and structures. So if you want to see the effect of the fluid on the structure, but you don't care about the fluid, but more of the impact on the structure. So you can actually use Abacus to simulate, as you can do a structural simulation where you're now talking about introducing fluid interaction as well. So I'll replay this video so you can clearly see what I was talking about before. So after this, it should be the soda can, and then, okay, the car crashed. It should show up now. Yeah, this one here is actually, we're talking about FSI, or fluid structure interaction, which is a great way to simulate, something very complex like this without having to model the fluid or having to do computational intensive CFD analysis. This is another example of what we call as it's a structural application, but the fluid inside the bottle, for example, is actually simulated using a technique called CEL, which is coupled Euler-Lagrangian methodology. Okay, so I don't want to spend time going through every single one of these functionalities, but these are basically the broad level functionalities that we get with Abacus. FE-safe analysis for durability, which is a great way to simulate high cycle fatigue, maybe even low cycle fatigue, or even well fatigue. We do have comprehensive meshing techniques. Oops, something went wrong here. Okay. So we also have access to a lot of meshing techniques as well as contact techniques. Here you can see a lot of different options that are available for creating your meshes, but also controlling the element formulations of these meshes. Here is an example of, and I hope you can appreciate that the use of general contact, right? In traditional contact, we have to do a guesswork. We have to specify upfront how the contacts are actually defined. But with Abacus general contact, you don't have to literally do anything. You just turn on the general contact option and the program takes care of all the physical interactions. So that's how powerful it is. One of the things that you get access to is also HPC or cloud compute or even local compute with HPC. A lot of times as engineers and analysts, we always know that RAM is never enough for large models. We also know that analysis takes way too long to run, and also you need to run multiple complex analysis at the same time. So with Abacus on the cloud, what we're talking about is being able to support the HPC infrastructure where the solver is actually scaling with more cores, right? So this example of an engine block is about 17 million degrees of freedom. With using the local machine, it takes about 48 hours to solve this problem using 8 cores. And then as you throw this problem onto the cloud, let's say with more cores, 36 cores takes about 10 hours to run. 144 cores takes about 2.5 hours to run. So clearly you can see almost like a 20x improvement in solve times, right? So something that takes 2 days now takes about a couple of hours to run. So that's the beauty of actually leveraging a solver that is scalable when you throw more number of cores. You also are getting access to more RAM to solve the same problem. But end of the day, we're talking about getting a faster turnaround in productivity when it comes to solve times. Here is just another example of a drop test on a camera. And you can see that with 1 core, it takes about an hour and 10 minutes to solve. With 18 cores, it just takes 8 minutes. Again, 8x speed up on the solve times. Again, just another example of how you can leverage multiple cores using the Abacus solver and get your problems solved much faster. All right, so that is kind of the structural portion of our simulation. Let's move on to fluids. Again, we're going to talk maybe I want to give you a high-level overview of some of the key features of the computational fluid dynamics tool, and let's go to the first. Okay, so I want to talk about comprehensive capabilities. Here, we are talking about fluid flow software, but again, we are looking at steady-state, transient, laminar, turbulent flows, transient. I'm not going to read everything verbatim, but just you can see that it's very comprehensive when it comes to capabilities, and even including something called mesh motion or rigid body motion, which is a great tool to use in fluid dynamics, especially when you have any kind of motion that happens within the fluid. So again, it's not just fluid flow, but it also supports heat transfer effects such as conduction, convection, radiation, and there are different. And we also have electronic component support such as PCB, heat sinks, TEC, joule heating, and so on. Okay. So it's a fully it's a full solution when it comes to computational fluid dynamics. Fluid flow plus heat transfer effects all can be simulated with this tool. One of the things I like about this tool is it's called body-fitted meshing techniques. Body-fitted meshing technique is a great way to mesh the geometry, the solid volume, the fluid volume, and also being able to control the boundary layer meshing. So here, for example, we are just using a hex mesh to mesh the volume of the fluid, and you can see that you can clearly see the boundary layers that you can actually control. You can specify how many boundary layers do you need, what is the size of the first characteristic boundary layer, and so on. So again, with this tool, you have full control over meshing and boundary layer meshing, as well as the good news is there are so many different types of meshing techniques available to mesh your fluid volumes. So one of the other aspect of this fluid solution is that it offers advanced turbulence modeling techniques. So it has SST K omega, which is great for internal flows, thermal external flows. It also has realizable K epsilon for most of the internal flows and thermal problems, and also Sparlet-Almaraz for external aerodynamics. Okay. One of the things that's also supported with these three turbulence model is intelligent near wall modeling. And what that means is that depending upon the coarseness of the mesh, the actual physics is solved in the boundary layer, and sort of making any approximations with the wall functions. So again, it's a great. So again, that we don't specify that as a user. The solver automatically picks what's the best methodology based on the mesh coarseness near the walls. Of course, like we talked about cloud computers with structural simulations, the same is available for computational fluid dynamics with this fluids tool. Just real quick, what you can do in terms of applications, when it comes to industrial equipment, you can see some examples of engine thermal performance, pump performance. We can predict derive pump curves from the simulations, any kind of HVAC or valve flows. We can easily do that with this particular tool. When it comes to high-tech electronics applications, you can actually not only simulate the fluid flow, in this case airflow, but also be able to optimize the fluid flow patterns, airflow patterns, being able to test multiple designs and find out what happens if you use a fan, if you don't use a fan, what happens if you use 10 fans. Obviously it's going to make a lot of noise, but is that going to keep the system cool? Absolutely, but the added noise may not be an advantage, and so you can scale back and say, let's test maybe 3 or 4 or 5 fans instead. Life sciences, you can see we can do a lot of different types of applications, from medical inhalers to peristaltic pumps to simulating blood flow through valves and so on. This is again consumer packaging goods like liquid filling or liquid pouring, bottle rinsing or bottle pouring type of applications, which could be very crucial to analyze when it comes to designing, let's say, soda bottles. This is another example of home and lifestyle, but again, this is more of an e-bike example. Analyzing the battery pack is really critical, right? You want to make sure that the battery pack module is kept cool at all times. It doesn't cause it's not a safety hazard where it overheats and then may be exploding. So we want to make sure that we can do battery thermal management as well So this tool allows you to do that. And then on the upper right side, you can see an example of a VOF application, which is more of, simulating the interface between, it's a flush valve flushing example, but it clearly shows that, it is a very complex type of physics where we are actually modeling both air and let's say water, and accounting for the interface, the surface tension effects or whatnot, between the two fluids of different types. This is a little bit larger, when it comes to construction, cities and territories, we're talking about very large scale problems. So this tool, which is called Fluid Dynamics Engineer, is a great one to use to actually capture these large scale problems. Why? Because it offers it offers support of multiple cores as well. So you can throw this problem on a 144 core machine or a cloud solve, and you can actually run these problems much faster today. These are just some of the other examples from marine and offshore, where we are talking about being able to control. These are just fluid flow around objects, but again, it makes a lot of sense to have a good measure on the boundary layer to capture the aerodynamics effect. The one here on the bottom right side, you can see that it's just an object floating on water. So the red is actually the water, and the blue part is actually air. And you can see that you can capture the small displacements, maybe the yaw, pitch, and roll of that object. And so that's actually simulated by a technique called as mesh motion, where we are simulating the rigid body motion of this object, and we can actually capture what effect, maybe there's a wave splashing across the object or on the object. We want to capture the loads because of that, or maybe you just want to see how the object has, what kind of yaw, pitch, and roll does the object have. And so mesh motion technology is a great way to analyze those rigid body motions combined with fluid flow. All right, so that is a quick introduction to some of the structural applications as well as the fluid applications using Abacus technology. Let's quickly take a look at one customer success story. Why is simulation important, right? So Caloi is a great customer here in Brazil, and they make a lot of these mountain bikes, road bikes, and now they're also into manufacturing of e-bikes. So they're located here in Brazil, but some of the business points, pain points are they have a very aggressive target. We're talking about almost 42 models in 2 years, and they have to satisfy a lot of safety standards. So it's even though it's just a bike, a frame that they are manufacturing, they have to make sure that the frame is subjected to drop testing and other types of tests according to the safety standards. And so one of the big issues with making different products, it's just frames, but different types of frames, very complex, very complicated features. One of the big pain points is it takes a long time to make prototypes. It's also not just a long time, but it is very, very expensive to make a lot of prototypes. But the goal is, how do we lightweight the design? How do we make sure it's strong enough, it's durable enough? So common challenges that you might also be having when you think about your own products, some of these challenges do resonate across a wide variety of industries, across a wide variety of engineering applications. So this is just a screenshot showing the different types of testing. So they do impact tests for falling mass or falling frame, and they do a lot of fatigue tests. Okay. So this is just showing one of the examples of how the testing is actually done. You can see they just drop the weight from a certain height on the frame and test if the frame can actually withstand that loading. So there are a lot of different types of testing they do. So the impact test for falling frame, again, is just, what if the frame falls from a certain height? What does that actually mean? Is it going to break or not? And they also do a lot of fatigue testing, which is basically repetitive loading. They're loading the structure, unloading the structure, and they want to see how many times that load comes on and off before the structure or the frame actually fails due to fatigue. So So one of the biggest challenges that we helped them with is that they wanted to pass the ISO 42210 impact test. And this is just showing a little bit more detail into how the structures tool powered by Abacus, it actually helped them simulate this with great, very, very easily. So when they simulated and saw that the test results the simulation results matches very well with the test results, they were like, yep, this is exactly the return on investment, in terms of, simulating something very complex, which they were not doing before, but now they were able to gain more confidence in using simulation as a tool to drive their design and decision process. So in the end, the outcome was very, so this is another challenge. I'm going to, just in the interest of time, let me just go through. So for Kaloi, the use of simulation and bringing simulation in-house, definitely helped with a lot of business benefits, right? Starting with cost of development was reduced by 50%. They passed the safety standard, with more simulations and less prototypes. They were able to accelerate the time to market by about, 25%, which means really something, in today's market, everybody's competitive. Everybody's trying to get the markets faster. Simulation is one of the great tools to use to get your products out to market much, much faster. And what is nice is something that actually took them 2 months to do, now is taking only 2 weeks to do. So that's a huge turnaround in productivity when it comes to using simulation. And a lot of the issues they were facing before, like they were able to identify, reduce, and fix, almost, and things like, scrap material and rework being done on the designs. They were able to reduce that effort by almost 50%. So with that, I would like to just kind of, a few call to action items is just if you go to our website, www.solidworks.com, there's a lot of information on all of our simulation solutions. So what I showed you today is a quick introduction to structures and fluids, but you can find a lot of other great information on our website, SolidWorks. So www.solidworks.com/simulation. The other thing we would like to actually also highly recommend and encourage you to do is, we have done a lot of SolidWorks Cloud Simulation Champion series over the last couple of years. So if you want to go ahead and see how our customers are using these tools to be successful with their businesses, please, so we have a whole series of cloud simulation webinars that we have actually put in place for you as well. So if you want to actually look at that, if you want to go to that website, you can scan this QR code. I'll leave it on for a few seconds, but then this will take you to the website where you can watch a lot of customer-facing webinars, webinars that are actually done by other customers like yourself. That's it. Thanks for your time. We really appreciate it, and hope you have a good day, and we'll talk next time.
Bom, que maratona, hein? Chegamos ao terceiro dia, o último dia do Good Morning Simulation. Estou aqui com meu parceiro de novo, Garbim. Bom, vamos fazer um resumão?
Vamos lá.
Né? Do que foi falado no primeiro dia, o que você apresentou. Primeiro, a gente teve uma edição extraordinária do 3DX Cast.
Isso.
Depois a gente teve uma apresentação tua. E aí fazer um resumo um pouquinho do que foi esse primeiro dia, o que foi o segundo dia, que a gente falou já um pouquinho na abertura. Isso. E o que a gente apresentou hoje também. Fala um pouquinho pra gente, conta um pouquinho, vamos fazer esse resumão aí.
Vamos lá. Resumindo, a Dassault tem 4 tipos de simulação que nós ofertamos para o mercado. Cálculo estrutural, escoamento de fluidos, eletromagnetismo e simulação do processo de injeção plástica. São 4. Claro, cada uma dessas 4 tem uma variação enorme de aplicações, de possibilidades e tudo mais. Só que, resumidamente, são 4. Então, no primeiro dia, nesse 3DX Cast, foi exatamente um bate-papo, pegando um pouquinho da experiência do Ramesh, do Hassan, mostrando como que eles aplicam esse tipo de tecnologia, auxiliam as empresas a aplicar esse tipo de tecnologia no mundo. Depois eu entrei falando sobre a parte da simulação do processo de injeção plástica. No segundo dia, tivemos o Hassan. O Hassan é um grande especialista nessa área de eletromag, com doutorado no assunto, falando um pouco de simulação de alta, baixa frequência, aplicações reais. E agora, no terceiro dia, o Ramesh, ele mostrou como os usuários SolidWorks, o nosso querido SolidWorks, podem se beneficiar também utilizando simulação dentro do mesmo ambiente, tanto a parte de cálculo estrutural, linear, não linear, estático, dinâmico, fadiga, otimização estrutural, tudo mais dentro do SolidWorks, como também essa parte de escoamento de fluidos, fluidos compressíveis, incompressíveis, fluidos newtonianos, não newtonianos, ou seja, os mais diversos tipos de aplicação dentro do SolidWorks.
Legal. Bom, galera, a gente está chegando ao final, como eu disse. Eu primeiro quero que o pessoal que está fazendo a edição para a gente coloca aqui no lettering, pode colocar, tá? O e-mail do Leandro, leandro.garbin@3ds.com, certo?
Isso.
Beleza, vai estar aqui no lettering, em algum lugar aqui no GC. Mas também vocês podem procurar suas revendas do seu país, da sua região. A gente tem um exército, né?
São 26 revendas. 27 revendas para cobrir todo o mercado latino-americano.
Então, assim, esse exército de pessoas está pronto para te atender, né? Esse cara aqui, cada hora está num lugar, trabalhando com eles, fazendo treinamento, apresentando. Então, o nosso objetivo é trazer conhecimento, dividir esse conhecimento com vocês e mostrar para vocês o quão importante é trabalhar com simulação, quão importante isso é aliado, por exemplo, ao SolidWorks, o quanto isso pode facilitar a sua vida, reduzir custos e melhorar a sua eficiência.
É isso aí.
Se vocês tiverem qualquer dúvida, entre em contato com a gente, entre em contato com a sua revenda, a gente está aqui para atender vocês. Mais uma vez, obrigado por participar da primeira edição do Good Morning Simulation. Garbin, obrigado por trazer esse projeto para a América Latina. Vamos para o próximo.
Eu que agradeço o suporte. Pessoal, espero que tenham gostado do conteúdo. A gente aqui está à inteira disposição. Forte abraço.
Valeu.